Good afternoon. I'm Saritha Kumari, working in Institute of Aeronautical Engineering College, Assistant Professor, Dundigal, Hyderabad. The course under the course continuation of my previous lectures under the course performance of transmission lines and cables. Today's topic is the lecture performance of long transmission lines. So lecture number 27. So it is mapped to course outcome 3. So this is a long transmission line. The diagram we see here, a long transmission line is shown here. It's equivalent circuit. So we know that a long transmission line means where all the parameters, resistance, inductance and capacitance are uniformly distributed along the total length of the line. So here the long transmission line is shown with the sending end voltage and sending end current Vs and Is, and at the receiving side where the load is connected, the receiving end voltage, that is nothing but load voltage Vr, and its current corresponding current is IR. So and here see that we see other parameters. Okay, we'll see what are those parameters. Here it is shown in the diagram. So basically it is defined, let small z be the series impedance per unit length, small z be the series impedance per unit length, and small y be the shunt admittance per unit length, small y be the shunt admittance per unit length, and small l be the length of the line. So accordingly, small z into L is nothing but total series impedance of the line, that is denoted with capital Z, and small y into L, that is nothing but total admittance of the line, which is denoted with capital Y. So initially these are the parameters defined. So here we see in the diagram where L is represented, the total length of the line, and see that what are this x, okay, and dx then. So here consider that. So this is what it is mentioned, taking receiving end is a reference. So that is always how it is. So they take receiving end is a reference, general receiving end voltage. So then let a distance of x meters. So initially from the receiving end they defined initially x distance of x meters, and after that they consider a small differential length dx. So they considered a small differential length dx at a distance of x meters, okay, from the receiving end. So that is what it is shown in the diagram. So at a distance from the receiving end, at a distance of a small differential length dx is taken at a distance of x meters. Now at a distance of x meters, the corresponding voltage and corresponding current is taken as Vx and Ix at a distance of x meters, and at a distance of x plus dx, at a distance of x plus dx, the voltage, corresponding voltage and current in the line is given by Vx plus dVx, Ix plus dIx, okay, at a distance of x plus dx. Okay, that is what it is mentioned here, the third point. Okay, at a distance of x meters, the voltage and current Vx and Ix. Then at a distance of x plus dx, voltage is Vx plus dVx, current is Ix plus dIx. Now at that point, with respect to that small differential length dx, it is written from based on Ohm's law, V is equal to IR. So it is given as V, okay, dVx is equal to okay, with respect to that small differential length dx. So the voltage is given by differential voltage. So small voltage dvx is equal to ix into what is a total impedance, series impedance of the line, z dx. Okay, so that is what we see in the diagram also. So with respect to this small differential length dx, the impedance is z dx and admittance is y dx. So dvx is given by ix into ix into z dx, and dix is given by, okay, we know that I is equal to, in terms of admittance, v into y, right? So dix is equal to vx into what is our corresponding admittance, y dx, right? So that is given by vx into y dx. Now, so after writing these two, write down what is dvx by dx. So from the first one, okay, that is based on Ohm's law, dvx by dx is equal to zix, and from the second equation, dix by dx is equal to y vx. Okay, say that equation 1 and equation 2. Equation 1 and equation 2. Now differentiate equation 1. Differentiating equation 1 with respect to x, we obtain okay, d square vx by dx square is equal to z dix by dx. Okay, z is a impedance of the line, so it doesn't change with respect to, okay, variation, differentiation. So dix by dx. Say that equation number 3. Now substitute from the equation 2 here. From the equation 2, substitute what is dix by dx. So from that it is obtained as d square vx by dx square is equal to, okay, z into y vx, right? So in place of this, okay, substituted. What is that? Y into vx, right? So y vx into z, that is written as yz vx. Say that equation number 4. So say that equation number 4. Now, so this is a second order differential equation. Okay. So in terms of vx, varying with respect to x. So the solution, okay, so that is what it is mentioned here. Equation 4 is a linear differential equation whose general solution can be written as follows. Okay, the general solution for this equation is given by vx is equal to, so okay, constant c1 into e power gamma x plus c2 e power minus gamma x. Okay, so that is a general solution for the equation number 4, where c1, c2 are constants. Okay, arbitrary constants to be, which are need to be evaluated. And what is gamma? It is given by square root yz, small y into small z, and it is called, gamma is called propagation constant. Okay, so say that they have given equation numbering. So this one equation vs equation number 5, and gamma is given square root yz, say that equation number 6. Now differentiating equation 5 with respect to x. So differentiating equation 5 with respect to x. So dvx by dx is equal to c. Okay, what we will get? We're differentiating with respect to x, right? So what it will become? E power gamma x. E power differentiation of e power gamma x is e power x into whatever the coefficient of that x. So we have gamma. So c1 gamma into e power gamma x. c1 gamma into e power gamma x. Okay, then e power minus gamma x becomes what? Minus gamma into e power minus gamma x. So minus c2 into finally it is C2 into gamma into e power minus gamma x, and which is also equal to what from the first equation. So we know that dvx by dx is equal to, okay, z into ix, right? So that is a, okay, equation. Now after from the equation 5 differentiation, now written what is ix from this. So ix is given by from here, okay, c1 by, okay, what we will get, ix is given by c1 by zc into e power gamma x minus c2 by, so from this, okay. Now what is this new one, zc? Okay, this zc is given by square root of z by y, square root of z by y, small z by small y, and it is named as, it is called as characteristic impedance of the transmission line. Okay, characteristic impedance of the transmission line. So that is how the ix equation, say that equation number 7. Okay, and this zc is square root small z by small y, say that equation number 8. Okay, so these are the equations for vx and ix. Anyway, finally we want to calculate, okay, this constants, okay, c1 and c2. Then finally, okay, we'll get the equations of the voltage and current. So that is how, see that how they obtain. See here, consider, okay. So using line end conditions, using transmission line end conditions. So that is when x is equal to 0, when x is equal to 0, what is voltage, what is current? V is nothing but, okay, we have taken receiving end is a reference, right? And x is defined at a distance of receiving end. Okay, x is a distance from the receiving end. So when x is 0, what is V? VR. What is current? IR. Okay, voltage is, okay, receiving end voltage. That means Vx is equal to VR and Ix is equal to receiving end current IR. Now from the okay, substitute this, okay, substitute this in equations 5 and 7. Okay, what is equation 5 and 7 from the previous slide? Equation 5 is the Vx equation and 7 is the Ix equation. So from that okay, Vx is nothing but VR, right? So VR is equal to C1 plus C2 from the equation 5. Yes or no? So because x is 0, e power 0 is 1, right? E power minus 0 means 1 by e power 0. So 1. So is C1 plus C2. VR is equal to C1 plus C2. And what is IR? IR is nothing but, so e power 0 1, C1 by ZC. Okay, again. So both are okay, C1 by ZC minus C2 by ZC. So ZC is written out of the, okay, from both it is common. So it is written 1 by ZC into C1 minus C2. Now we can solve what is C1, C2 from these two equations. Okay, so after solving these two, C1 is obtained 1 by 2 into VR plus ZCIR and C2 is given by 1 by 2 into VR minus ZCIR. Okay, now substitute this C1, C2 in equations 5 and 7. Substitute C1, C2 in equations 5 and 7. Okay, so now what is voltage equation, what is current equation? We know that, right? C1 into e power gamma x, okay, plus C2 into minus C2 into e power, okay, Vx is given by C1 e power gamma x plus C2 into e power minus gamma x. So that's why in place of C1, okay, VR plus ZCIR by 2. In place of C2. VR minus ZC IR by 2. Say that equation number 9. Equation number 9. And Ix is given by, okay, 1 by ZC into C1 minus C2, right? Sorry, Ix is given by C1 by ZC, okay, C1 by ZC. So that's why it is written as C1 by ZC. So ZC gets cancelled here for IR, and for VR it becomes VR by ZC. So VR by ZC plus IR by 2 for e power gamma x, then minus, okay, minus C2 by ZC, right? So VR by ZC minus IR by 2 into e power minus gamma x. Say that equation number 10. So say that this is equation number 10. Now, okay, finally we have obtained voltage and current equations, okay, in terms of known parameters. So finally see that the equations, so written, okay, in a simplified manner, this equation 9 and 10, okay. So taking this hyperbolic functions, okay, as a common term, see that, not common term. So written equation in terms of only in VR and IR, right? That is how the equations, transmission line equations, okay, voltage and current equations in terms of VR and IR. That's why, so what is VR? From the equation number 9, VR into e power gamma x plus e power minus gamma x by 2. And what is IR coefficient? ZC into, in brackets, e power gamma x by e power minus gamma x by 2. This is from equation number 9. Okay, equation number 9. So this is equation number 11. It is given. Then similarly Ix also. Ix is given as, written as VR into 1 by ZC into e power, in brackets, e power gamma x minus e power minus gamma x by 2 plus IR into e power gamma x plus e power minus gamma x by 2. So say that equation number 12. This is equation number 12. Now we know that, okay, this what is the hyperbolic function of this e power gamma x by e power minus gamma x by 2. So that's why these equations of Vx and Ix can be again rewritten now. Vr into, so this is nothing but e power gamma x minus gamma x by 2 means cos h gamma x, okay. And e power gamma x minus e power minus gamma x by 2 is nothing but sin h gamma x, okay. And Ix equation, okay, VR into 1 by ZC into, okay, so first they're writing IR coefficient, IR term. So IR into this is nothing but cos h gamma x, and VR into 1 by ZC into sin h gamma x. Now finally see that how it is finally simplified. Okay, when x is equal to L, when the distance x meters is nothing but is equal to total length of the line, if it is taken, then what is Vx? Vx becomes Vs and Ix becomes Is. Okay, so x is taken from the reference point receiving end. Okay, if we take from the receiving end to the other end, the total length, what is that? V becomes Vs and I becomes Is. So finally these two equations, that means Vx is replaced with Vs now. So Vs is equal to Vr cos h gamma L. Okay, so x is substituted with L, and I plus IR ZC sin h gamma L. Say that equation number 13, and Is is equal to IR cos h gamma L plus VR 1 by ZC sin h gamma L. So finally say that equation number 13 and 14, and these are the equations, okay, sending and voltage and current equations in terms of receiving end voltage and receiving end current. Okay, and line parameters, RLC, resistance, inductance, capacitance. So this is how finally for the long transmission line, the voltage, sending end and receiving end voltage and current equations are finally obtained. Okay, finally obtained. Now from the equivalent circuit, like for medium transmission line, short transmission line, how it is derived. Now writing this in matrix form. So writing these equations, two equations in matrix form. So on the left side, Vs and Is, and on the right side, what are the two things? Voltage currents are VR and IR, and what are the coefficients? Okay, what are the coefficients? So this is the first coefficient in the matrix, second coefficient down, this is the one. Okay, so that is how the, so written cos h gamma l in the matrix, Zc sin h gamma l, and the down 1 by Zc sin h gamma l, right? Sin h gamma l and cos h gamma l. Now, so compare this with the standard equations. Okay, what are the, generally we know that ABCD constants are used to represent the performance of transmission line. That's why compare this equation 15, okay, written in matrix form with the ABCD constants. Okay, so Vs Is is equal to ABCD into VR IR. What is A? Cos h gamma l. What is D? That is also same as cos h gamma l. What is B? Zc sin h gamma l. What is C? 1 by Zc sin h gamma l. Say that equation number 17. Now also we verify. Okay, A is equal to D. Okay, so A constant is equal to D constant, which is equal to cos h gamma l, and AD minus BC. Okay, second condition, AD minus BC, cos h square gamma l minus sin h square gamma l. So that is equal to 1. We know that. So that's why AD minus BC is equal to 1. So second condition also satisfied. So that's why we say that, we can say that the equations we have derived are right equations, correct equations. Okay, because these two conditions are satisfied. Whatever the equations, okay, we have derived for Vs and Is in terms of VR and IR, okay, those equations are correct equations because they are satisfying these two conditions. A is equal to D and AD minus BC is equal to 1. Now, we can write down VR and IR equations also from the above. How? Okay, it is by inverting the above relation. So VR and IR is equal to D minus B minus C A Vs and Is. So that is how simply we can write down VR and IR equations also in terms of Vs and Is. Now, one more point here, how to evaluate the ABCD constants for the long transmission lines. Okay, we'll do later a problem also based on the long transmission lines. Okay, to know the performance of the line. That means we can indirectly we say calculating ABCD constants of the line also. Okay, so here how to, for the long transmission line, they are given like this. Okay, so calculating ABCD constants, first method, okay, knowing that gamma is square root small y small z, okay, which is also given by in terms of real and imaginary component alpha and beta like this. Okay, so now okay, this is a basic idea. Now how to calculate ABCD constants for the long transmission line method. First method is, okay, writing cos h gamma l. We know that gamma is nothing but just now it is mentioned alpha plus j beta, right? So cos h a plus b, this is a basic mathematical expansion. Okay, okay, so This is one thing, and this is the first one for cos, and sin h gamma L is, okay, this is a expansion. So this is how, okay, it is how one method we can calculate ABCD constants. Second method, okay, we know that cos h gamma L, another expansion, 1 plus x square by 2, x square by x power 4 by 4 factorial. Okay, so x means here gamma L, right? So that's why it is written, okay, 1 plus x square by 2 factorial means gamma square L square. Next, x power 4 means gamma, okay, which is equated to, okay, approximated to 1 plus yz by 2. Okay, because we know gamma is square root small y small z, right? Into small L square ante small y into small z into small L becomes total y, capital Y. Similarly, x z. So only first term is considered. Okay, so approximated to 1 plus yz by 2, capital Y, capital Z. Then similarly, what is sin h gamma L expansion? This is another expansion for sin h gamma L. X plus x cube by 3 factorial plus x power 5 by 5 factorial. Okay, that is how finally it is simplified. Okay, approximated to under root capital YZ into 1 plus capital YZ by 6. So these are the cos h gamma L, sin h gamma L expansions. So for a given data using transmission line total impedance and admittance, we can calculate cos h gamma L, sin h gamma L, so that we can calculate ABCD constants of the line. Okay. And they are telling this is approximation, right? Here they approximated. So it is approximation is convenient, quite accurate for lines up to 400 to 500 kilometers. There is one more method, say that that is given method 3. Cos h gamma L means cos h gamma L plus j beta L, which is also nothing but e power x plus e power minus x by 2, right? So this is another expansion for cos h gamma L, and sin h gamma L, this is expansion. So like this also we can calculate. Okay, we can calculate cos h and sin h gamma L. That means we are calculating ABCD constants. So these are the how for long transmission lines we can calculate ABCD constants. So next, this is for okay, for this lecture, this is how for the performance of long transmission lines is explained. Okay, its equations are written and ABCD constants are written. Okay, so these are the references. Okay, textbooks, and that's all for this lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.